Look up at the night sky and you'll see it a shimmering river of stars stretching across the darkness. That's the Milky Way, our home in the vast cosmos. But what if I told you that this galaxy, so familiar yet so mysterious, holds secrets that defy everything we think we know? For instance, did you realize that the Milky Way is built on a foundation of something invisible, something we've never seen but know is there? Or that it's been devouring smaller galaxies for billions of years, shaping itself into the cosmic giant we see today? In this video, we're diving into 25 astonishing secrets of the Milky Way, facts so mind-blowing they'll leave you in awe. From the supermassive black hole lurking at its heart to the ancient stars that tell the story of its birth, we're uncovering the hidden wonders of our galaxy. So get ready to see the Milky Way in a whole new light, because by the end of this journey, you'll realize just how little we truly know about the universe we call home. Let's begin. Now, turning to the first secret, let's explore something that's both fascinating and elusive: the Milky Way's invisible halo. This halo is made up of dark matter, a mysterious substance that doesn't emit, absorb, or reflect any light, making it completely invisible to our eyes and even our most advanced telescopes. Yet it plays a crucial role in holding our galaxy together. Without this massive, unseen presence, the stars, planets, and dust that make up the Milky Way would simply fly apart. Scientists estimate that this dark matter halo is about 10 times more massive than all the visible matter in the galaxy combined. It's like the hidden skeleton of our cosmic home, providing the gravitational glue that keeps everything in place. But studying something we can't see comes with its own set of challenges. Researchers rely on indirect evidence, such as the way stars move within the galaxy and how light bends around massive objects, to map this invisible structure. The discovery of dark matter has revolutionized our understanding of galactic formation and evolution, but it also raises more questions than answers. What exactly is dark matter made of? How does it interact with the visible universe? These are some of the biggest mysteries in modern astronomy, and the Milky Way's invisible halo is at the heart of it all. As we continue to probe the depths of our galaxy, this unseen force reminds us just how much of the universe remains hidden from view, waiting to be uncovered. Shifting our focus to the next astonishing secret, let's dive into the Milky Way's history of galactic cannibalism. Yes, our galaxy has a long-standing habit of devouring smaller galaxies, a process that has significantly shaped its current form. One of the most notable remnants of these cosmic feasts is the Gaia Enceladus galaxy, which was absorbed by the Milky Way billions of years ago. This ancient collision left behind a trail of stars and other materials that astronomers have been able to trace, revealing the turbulent history of our galactic home. The Milky Way's gravitational pull is so immense that it can tear apart smaller galaxies, drawing their stars, gas, and dust into its own structure. Over time, these mergers have added to the Milky Way's mass and complexity, influencing everything from the distribution of stars to the formation of new celestial bodies. This process isn't just a relic of the past, it's still happening today. The Milky Way continues to interact with nearby dwarf galaxies, such as the Sagittarius dwarf spheroidal galaxy, which is slowly being absorbed. These cosmic collisions are not destructive in the traditional sense. Instead, they are a form of galactic evolution, reshaping and enriching the Milky Way over billions of years. Understanding this process gives us a deeper appreciation of the dynamic and ever-changing nature of our galaxy. It's a reminder that even the vast, seemingly unchanging Milky Way has a dramatic history of growth and transformation, driven by forces that are as awe-inspiring as they are invisible to the naked eye. Now, turning to the heart of the Milky Way, we encounter one of the most mysterious and powerful objects in the universe, Sagittarius, a star, the supermassive black hole at the center of our galaxy. With a mass equivalent to more than 4 million suns, This colossal entity exerts an immense gravitational pull, influencing the motion of stars and gas clouds within its vicinity. Despite its overwhelming presence, Sagittarius, a star, was not directly observed until recent decades. Its existence was first inferred through the erratic movement of stars nearby, which were found to orbit an invisible, incredibly dense object. Advanced telescopes and groundbreaking technology eventually allowed scientists to capture the first image of its event horizon in 2019, a monumental achievement in astrophysics. Sagittarius, a star, plays a critical role in maintaining the structure and stability of the Milky Way. Its gravitational force helps shape the galaxy's central region, keeping stars and gas in an intricate dance around its core. Without it, the galaxy as we know it would unravel, losing the delicate balance that holds its vast expanse together. This supermassive black hole also occasionally flares up, emitting bursts of energy that ripple through the galaxy, influencing star formation and the behavior of cosmic matter. Its presence is a testament to the dynamic and often violent processes that govern the cosmos. Understanding Sagittarius, a star, not only sheds light on the nature of black holes, but also deepens our appreciation for the complex forces that shape our galactic home. It's a reminder that even the heart of the Milky Way holds secrets waiting to be uncovered, secrets that challenge our understanding of the universe and our place within it. Now shifting our gaze to the vast expanse of the Milky Way, we encounter a mystery that has puzzled astronomers for decades: the true number and structure of its spiral arms. These sweeping arms, adorned with billions of stars, gas, and dust, are iconic features of our galaxy, yet their exact nature remains elusive. For years, scientists have debated whether the Milky Way has 2, 4, or even more spiral arms. Observations from different wavelengths of light, from infrared to radio, have provided conflicting evidence, deepening the enigma. The challenge lies in our position within the galaxy itself. Being inside the Milky Way makes it difficult to map its structure with precision, as we can only see a small portion of it at a time. Recent advancements in technology, such as the Gaia Space Observatory, have begun to shed light on this puzzle. By precisely measuring the positions and movements of stars, astronomers are piecing together a clearer picture of the spiral arms. Interestingly, these arms are not static. They rotate around the galactic center, with stars and gas flowing in and out of them over time. This dynamic process plays a crucial role in the galaxy's evolution, influencing star formation and the distribution of matter. The mystery of the Milky Way's spiral arms reminds us that even the most familiar features of our galaxy hold secrets waiting to be uncovered. Understanding their true nature not only deepens our knowledge of the Milky Way, but also offers insights into how spiral galaxies form and evolve across the universe. As we continue to explore this cosmic puzzle, we are reminded that the Milky Way is far more complex and fascinating than we ever imagined. Now turning our attention to the heart of the Milky Way, we discover a fascinating feature that shapes much of the galaxy's activity: the galactic bar. This elongated, bar-shaped structure stretches across the central region of the Milky Way, acting as a gravitational hub that influences the movement of stars, gas, and dust. Unlike the graceful spiral arms, the bar is a dense, bustling environment where forces of gravity guide the flow of matter. This central bar plays a critical role in star formation. As gas and dust are funneled toward the bar's ends, they become compressed, triggering the birth of new stars. These regions, known as star-forming nurseries, are some of the most active areas in the galaxy. The bar also acts like a cosmic conveyor belt, transporting material inward toward the supermassive black hole at the galactic center and outward to the spiral arms, ensuring a continuous cycle of creation and renewal. But the galactic bar doesn't just influence matter. It affects the motion of stars as well. Stars caught in the bar's gravitational pull follow elongated, oval-shaped orbits, creating a dynamic dance that keeps the galaxy's core alive with activity. This motion helps distribute energy and material, shaping the Milky Way's evolution over billions of years. Interestingly, the presence of a galactic bar isn't unique to the Milky Way. Many spiral galaxies in the universe feature similar structures, suggesting they play a universal role in galactic dynamics. Understanding our own galactic bar provides valuable insights into how galaxies form, evolve, and maintain their intricate balance. As we continue to study this central feature, we uncover yet another layer of the Milky Way's complexity, reminding us that even the most familiar parts of our galaxy hold mysteries waiting to be explored. Now shifting our gaze to the outer reaches of the Milky Way, we encounter a cosmic phenomenon that defies expectations: hypervelocity stars. These extraordinary stars are hurtling through space at such incredible speeds that they can break free from the galaxy's gravitational grip. Imagine a star traveling so fast it's essentially on an interstellar escape route, leaving the Milky Way behind forever. So where do these rogue stars come from? Many are born from dramatic encounters with the supermassive black hole at our galaxy's center. When a binary star system, two stars orbiting each other, drifts too close to the black hole, its immense gravitational force can tear the pair apart. One star gets captured by the black hole, while the other is flung outward at mind-boggling speeds, sometimes exceeding 1,000 kilometers per second. This cosmic slingshot effect propels the star into the void between galaxies, where it embarks on a lonely journey through the cosmos. But hypervelocity stars aren't just cosmic oddities, they're invaluable tools for understanding galactic dynamics. By tracking their trajectories, astronomers can map the distribution of dark matter in the Milky Way, as the stars' paths are influenced by this invisible force. These stars also offer clues about the environment near the supermassive black hole, shedding light on the extreme conditions that shape our galaxy's core. Interestingly, not all hypervelocity stars originate from the galactic center. Some may be the remnants of past interactions between the Milky Way and smaller galaxies, ejected during violent collisions. Others might have been accelerated by supernova explosions, their shockwaves giving nearby stars a powerful cosmic kick. Each hypervelocity star tells a unique story, offering a glimpse into the forces that govern our galaxy's evolution. As these stars race beyond the Milky Way's boundaries, they remind us of the immense power and unpredictability of the universe. They're a testament to the dynamic, ever-changing nature of galaxies, where even the smallest interactions can have far-reaching consequences. Hypervelocity stars are not just escaping the Milky Way, they're helping us unravel its mysteries, one high-speed journey at a time. Now turning to another hidden force shaping our galaxy, let's explore the Milky Way's magnetic field. Though invisible to the naked eye, this magnetic field plays a crucial role in the cosmic dance of stars, gas, and cosmic rays. Picture it as a vast, intricate web stretching across the galaxy, guiding the movement of charged particles and influencing the birth of new stars. The Milky Way's magnetic field is surprisingly strong, though it varies in intensity depending on location. Near the galactic center, it's far more powerful, while in the outer regions, it weakens but still remains a significant force. This magnetic field doesn't just sit idly, it interacts with cosmic rays, high-energy particles that zip through space. The field acts as a cosmic shield, bending and redirecting these rays, which can otherwise be harmful to life and even disrupt star formation. But how do scientists study something they can't see? Mapping the Milky Way's magnetic field is no easy task. Astronomers rely on the polarization of light emitted by stars and dust. As light travels through the galaxy, it gets twisted by the magnetic field, leaving behind subtle clues about its strength and direction. Radio telescopes are particularly useful for this, as they can detect these polarized signals and piece together a map of the magnetic landscape. One of the most fascinating aspects of this magnetic field is its role in star formation. Dense clouds of gas and dust, the birthplaces of stars, are often threaded with magnetic lines. These lines can either help or hinder the collapse of gas into new stars. In some cases, the magnetic field resists the gravitational pull, slowing down the process. In others, it channels the gas into specific regions, accelerating the birth of stars. This delicate balance between magnetism and gravity is key to understanding how stars come to life. The Milky Way's magnetic field is also a testament to the galaxy's dynamic nature. It's not static, it evolves over time, shaped by supernova explosions, stellar winds, and the movement of gas and dust. Each of these events leaves its mark, weaving a complex and ever-changing magnetic tapestry. So, while we can't see this magnetic field directly, its influence is everywhere, from the behavior of cosmic rays to the formation of stars. It's yet another reminder of the unseen forces that shape our galaxy, making the Milky Way not just a collection of stars, but a living, breathing entity with its own invisible heartbeat. Shifting our gaze to another striking feature of our galaxy, let's uncover the mystery of the Fermi Bubbles. These colossal structures stretch tens of thousands of light years above and below the Milky Way center, resembling two enormous balloons filled with gamma rays. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these bubbles have puzzled scientists ever since, as they hint at dramatic events in the galaxy's past. The Fermi bubbles are filled with high-energy particles, emitting gamma rays that make them visible to specialized telescopes. What's even more fascinating is their sheer size. Each bubble spans roughly 25,000 light-years, dwarfing many other structures in the Milky Way. Their discovery was a game-changer, as they revealed a previously unknown aspect of our galaxy's behavior. But what caused these massive bubbles to form? One leading theory points to the supermassive black hole at the center of the Milky Way, Sagittarius, a star. Scientists think that millions of years ago, this black hole may have had a period of intense activity, devouring large amounts of matter and releasing enormous bursts of energy. These violent outbursts could have ejected streams of gas and particles into the galaxy's outer regions, creating the Fermi bubbles we see today. Another possibility is that the bubbles were formed by a series of supernova explosions in the galactic center. When massive stars reach the end of their lives, they explode with incredible force, releasing vast amounts of energy and matter. If enough of these explosions occurred in a relatively short time, they could have propelled gas and particles outward, shaping the bubbles over time. While both ideas have their merits, the true origin of the Fermi bubbles remains an open question. What's clear, though, is that they serve as a cosmic reminder of the Milky Way's dynamic and sometimes explosive nature. They also highlight the interconnectedness of phenomena in our galaxy, from the activity of its central black hole to the life and death of its stars. As we continue to study these mysterious structures, we're not just uncovering the secrets of the Milky Way, we're piecing together the story of how galaxies evolve over billions of years. The Fermi bubbles are a testament to the hidden forces at work in our cosmic neighborhood, offering a glimpse into the powerful processes that shape the universe around us. Now turning to another fascinating process shaping our galaxy, let's explore the concept of the galactic fountain. Imagine a cosmic cascade where gas is ejected into space, only to rain back down, enriching the Milky Way with the building blocks of new stars and planets. This phenomenon is driven by the explosive power of supernova, the dramatic deaths of massive stars. When a supernova occurs, it sends shock waves through its surroundings, propelling enormous amounts of gas and dust outward from the galactic disk. This material can travel thousands of light years into the halo, the vast region surrounding the Milky Way. Over time, gravity pulls this gas back down, creating a cycle that resembles a fountain. This process plays a crucial role in the life of our galaxy. As the gas falls back, it carries with it heavy elements forged in the hearts of stars and during supernova explosions. These elements, such as carbon, oxygen, and iron, are essential for forming new stars, planets, and even life itself. Without this recycling mechanism, the Milky Way would gradually run out of the raw materials needed for star formation. The galactic fountain also helps regulate the temperature and density of the interstellar medium, the space between stars. By redistributing gas and energy, it creates regions where new stars can ignite while cooling other areas, maintaining a delicate balance within the galaxy. This continuous cycle of ejection and return is a testament to the dynamic nature of the Milky Way. It shows how even the death of stars contributes to the birth of new ones, ensuring that our galaxy remains a vibrant and evolving place. So, the next time you gaze at the night sky, remember that the stars you see are part of an intricate cosmic dance, fueled by the awe-inspiring processes of the galactic fountain. Now, shifting our focus deeper into the heart of our galaxy, we uncover the secrets of the Milky Way's ancient core. Nestled near the center of the galaxy lies a collection of some of the oldest stars in existence, shining like cosmic relics from a time long before our solar system even formed. These ancient stars are thought to be more than 13 billion years old, making them some of the first to light up the universe after the Big Bang. Their presence offers astronomers a rare glimpse into the earliest stages of the Milky Way's formation. These stars are part of a dense region known as the Galactic Bulge, a tightly packed area surrounding the supermassive black hole at the center. Their composition is strikingly different from younger stars like our Sun. They contain far fewer heavy elements, which tells us they were born in an era when the universe was still young and pristine, before generations of stars had produced and scattered these elements through supernova explosions. Studying these ancient stars helps scientists piece together the Milky Way's origin story. It's believed that the galaxy began as a small, dense cluster of stars and gas, gradually growing over billions of years through mergers with other galaxies and the accumulation of new material. The oldest stars in the core serve as cosmic time capsules, preserving the conditions and processes that shaped the Milky Way in its infancy. One particularly fascinating aspect of these stars is their motion. Unlike younger stars that orbit in the galaxy's disk, these ancient stars have more chaotic, elongated orbits. This suggests that the early Milky Way was a much more turbulent and dynamic place, with frequent gravitational interactions and collisions. By analyzing these ancient stars, astronomers can also refine their understanding of how galaxies form and evolve across the universe. They provide a window into a time when the cosmos was still taking shape, offering clues about the forces that shape not just the Milky Way but all galaxies. So, while the Milky Way's ancient core may seem like a distant and mysterious place, it holds the key to understanding our galaxy's past. These ancient stars remind us that the Milky Way has a long and complex history, one that continues to unfold as we uncover its secrets. Now, diving into another cosmic puzzle, we explore the missing satellite problem, a mystery that challenges our understanding of the Milky Way and its surroundings. According to the widely accepted theory of dark matter, our galaxy should be surrounded by hundreds of small satellite galaxies. These are tiny galaxies that orbit the Milky Way, held in place by its immense gravitational pull. However, when astronomers look into the night sky, they find far fewer than expected. This discrepancy between prediction and observation has puzzled scientists for decades. One leading explanation for this missing satellite problem involves the nature of dark matter itself. It's possible that the properties of dark matter are slightly different than we currently assume. For example, if dark matter particles are warmer or more energetic than predicted, they might not clump together as easily, resulting in fewer small galaxies forming. Another theory suggests that these satellites do exist, but they are too faint or diffuse to detect with current technology. some of these galaxies may be composed mostly of dark matter, making them nearly invisible to our telescopes. A third possibility is that interactions with the Milky Way have disrupted or destroyed many of these satellites over time. As smaller galaxies orbit the Milky Way, they can be torn apart by gravitational forces, their stars scattered across the galaxy's halo. This would leave behind only a fraction of the expected satellites, making the ones we see today the survivors of a cosmic battle. Interestingly, advancements in observational technology are beginning to shed light on this mystery. Recent surveys have uncovered a few ultra-faint satellite galaxies that were previously undetected, hinting that there may be more waiting to be discovered. These findings suggest that the missing satellite problem might not be a failure of the dark matter theory, but rather a limitation of our ability to observe the universe in its full complexity. The missing satellite problem is more than just a cosmic curiosity. It has profound implications for our understanding of how galaxies form and evolve. By solving this mystery, scientists hope to refine their models of dark matter and gain deeper insights into the structure of the universe itself. As we continue to explore the cosmos, this puzzle reminds us that even our most well-established theories are still a work in progress. Now shifting our gaze to the outer reaches of the Milky Way, we uncover a fascinating anomaly, the warped disk of our galaxy. Unlike the flat, pancake-like shape often depicted, the outer edges of the Milky Way's disk are twisted and bent, giving it a slightly distorted appearance. This warping is thought to be caused by gravitational interactions with neighboring galaxies or the influence of dark matter, though the exact mechanisms remain a subject of ongoing research. One theory suggests that the gravitational tug of nearby galaxies, such as the Large and Small Magellanic Clouds, could be pulling on the Milky Way's outer disk, causing it to warp over time. Another possibility is that dark matter, which permeates the galaxy, could be exerting uneven forces, distorting the disk shape. Regardless of the cause, this warping is a reminder of the dynamic and interconnected nature of galaxies in the universe. The warped disk poses unique challenges for astronomers trying to map the Milky Way. Traditional models assume a flat disk, but the warping complicates measurements of distances and positions of stars, gas, and other celestial objects. This has led to discrepancies in our understanding of the galaxy's structure, particularly in its outer regions. Advances in technology and new observational techniques, however, are helping scientists account for this distortion and refine their maps. Interestingly, the warped disk also offers clues about the Milky Way's history and its interactions with its cosmic neighborhood. By studying the degree and direction of the warp, researchers can infer the forces that have shaped the galaxy over billions of years. This, in turn, provides insights into the distribution of dark matter and the gravitational dynamics of the local group of galaxies. As we continue to explore the Milky Way's warped disk, we gain a deeper appreciation for the complexities of our galactic home. This subtle distortion reminds us that even the most familiar cosmic structures can hold surprises, challenging our assumptions and expanding our understanding of the universe. Now shifting our focus inward, we come to a concept that might redefine how we think about life in the universe, the galactic habitable zone. Just as planets have a habitable zone where conditions are right for liquid water and potentially life, the Milky Way itself has regions that are more conducive to life than others. This idea challenges us to consider not just where life could exist on a planetary scale, but also where it might thrive on a galactic scale. The galactic habitable zone refers to a specific area within the Milky Way where the conditions are just right for life-bearing planets to form and flourish. This zone is typically located in the middle regions of the galaxy, far enough from the chaotic center yet close enough to have the necessary resources for life. So, why is life less likely in other regions? Let's start with the galactic center. While it's a hub of activity, it's also a dangerous place. the intense radiation from the supermassive black hole, frequent supernova, and powerful cosmic rays make it inhospitable for life as we know it. On the other hand, the outer regions of the Milky Way lack the heavy elements essential for forming rocky planets and complex molecules. These areas are more sparsely populated with stars and have fewer of the building blocks needed for life to emerge. The galactic habitable zone strikes a delicate balance. It's far enough from the hazards of the center, yet enriched with the materials necessary for planet formation. This zone also benefits from a stable environment, with fewer catastrophic events that could wipe out emerging life. It's here, in this cosmic sweet spot, that we're most likely to find planets capable of supporting life. This concept not only helps us narrow down the search for extraterrestrial life, but also deepens our understanding of the Milky Way's unique structure. It's a reminder that the galaxy isn't uniform. It's a patchwork of environments, each with its own potential for harboring life. As we ponder the galactic habitable zone, we're reminded of how much there is still to discover about our place in the cosmos. This idea encourages us to look beyond individual planets and consider the broader galactic landscape in our search for life. Now turning to the broader cosmic picture, let's explore the Milky Way's place in its cosmic neighborhood. Our galaxy is part of a larger family known as the Local Group, a collection of over 50 galaxies bound together by gravity. Among these, the Milky Way and the Andromeda Galaxy are the two largest, with dozens of smaller galaxies orbiting them. This cosmic community is a bustling hub of activity, with galaxies influencing one another through gravitational tugs and interactions. At the heart of this neighborhood drama is the Milky Way's relationship with Andromeda. Located about 2.5 million light-years away, Andromeda is not just our closest galactic neighbor, but also our future partner in a cosmic dance. In about 4.5 billion years, the two galaxies are predicted to collide, merging into a single, larger galaxy. This event, far from being destructive, will be a spectacular transformation. Stars and gas clouds will be pulled into new orbits, triggering bursts of star formation and reshaping both galaxies into something entirely new. But why does this collision matter? For one, it's a reminder that galaxies aren't static. They evolve, interact, and change over time. The merger with Andromeda will mark a significant chapter in the Milky Way's history, one that will also affect its future structure and the distribution of stars within it. Interestingly, while galaxies collide, the vast distances between stars mean that individual stars are unlikely to crash into one another. Instead, the collision will create a stunning visual spectacle, with the two galaxies tangling and merging over billions of years. This cosmic event also offers a glimpse into the dynamic nature of the universe. Galaxies like the Milky Way aren't isolated islands. They're part of a larger web of interactions that shape their evolution. Understanding these processes helps us piece together the story of how galaxies form, grow, and transform over time. As we look ahead to the Milky Way's future collision with Andromeda, we're reminded of the interconnectedness of the cosmos. It's a story of change, evolution, and the ongoing dance of galaxies, a dance that will continue to shape the universe for billions of years to come. Now shifting our focus to the spaces between galaxies, let's uncover the mysterious intergalactic medium. Far from being empty, the vast expanses between galaxies are filled with a thin, almost invisible gas. This gas, though sparse, plays a crucial role in the life cycle of galaxies, including our Milky Way. The intergalactic medium is made up of hydrogen and helium, remnants from the early universe. This gas is so diffuse that it's often hard to detect, yet it's everywhere, connecting galaxies like an invisible web. The Milky Way, like other galaxies, interacts with this medium by pulling in gas to fuel star formation or expelling it through events like supernova explosions. This exchange of gas is vital for galactic evolution. When the Milky Way draws in gas from the intergalactic medium, it provides the raw material for new stars and planets. On the other hand, when stars die in supernova, they eject gas back into this medium, enriching it with heavier elements like carbon and oxygen. Over billions of years, this cycle of gas inflow and outflow shapes the Milky Way's structure and composition. The intergalactic medium also acts as a bridge between galaxies, enabling them to influence one another. For instance, when galaxies collide or pass near each other, they can pull gas from this medium or deposit it, altering their own evolution and that of their neighbors. This interconnectedness highlights how the Milky Way is part of a larger cosmic ecosystem, where even the seemingly empty spaces play a role. Understanding the intergalactic medium isn't just about studying gas, it's about tracing the flow of matter and energy that drives the evolution of galaxies. For the Milky Way, this medium is both a source of renewal and a reminder of its place in the vast, dynamic universe. Now turning to the bustling hubs of creation within our galaxy, we uncover the Milky Way star factories. These regions, teeming with gas and dust, are where the magic of star birth unfolds on a cosmic scale. One of the most famous of these stellar nurseries lies within the Orion Arm, a spiral arm of the Milky Way that's home to some of the most active star-forming regions known to astronomers. Here, vast clouds of hydrogen gas collapse under their own gravity, heating up until nuclear fusion ignites, giving birth to new stars. This process doesn't happen in isolation. Shockwaves from nearby supernova or the collision of gas clouds can trigger the formation of these stellar giants. It's a delicate balance of chaos and creation, where the right conditions lead to the birth of stars that may burn for billions of years. The Orion Nebula, a well-known star-forming region, is a prime example. This glowing cloud of gas and dust is a breeding ground for young stars, some of which are still surrounded by the disks of material that may one day form planets. It's a reminder that the Milky Way is not just a collection of stars but a dynamic ecosystem, constantly evolving and regenerating itself. What's fascinating is that the process of star formation isn't uniform across these regions. Some areas produce massive stars that burn brightly and die young, while others give birth to smaller, longer-lived stars like our own Sun. This diversity in star formation ensures that the Milky Way remains a galaxy of endless variety and wonder. Understanding these star factories is key to unraveling the Milky Way's past and future. They tell us how our galaxy has grown over billions of years and how it continues to shape the cosmic landscape around us. As we explore these regions, we're not just studying stars, we're witnessing the very essence of creation in action. Shifting our focus to the cosmic cycles that sustain our galaxy, we delve into the Milky Way's remarkable recycling system. This process is a testament to the galaxy's ability to repurpose material, ensuring that nothing goes to waste in the vastness of space. Here, the death of stars becomes the birthplace of new ones, creating an endless cycle of renewal. When massive stars reach the end of their lives, they often explode in spectacular supernova, scattering their enriched materials across the galaxy. These elements, forged in the hearts of stars, include heavy metals like iron and gold, which are essential for the formation of planets and even life itself. Planetary nebulae, the glowing shells of gas ejected by dying stars, also contribute to this cosmic recycling. Together, these phenomena provide the raw ingredients for the next generation of stars and planetary systems. This process isn't just a random scattering of debris, it's a carefully orchestrated dance. As these materials are ejected, they mix with the surrounding interstellar medium, the vast clouds of gas and dust that fill the galaxy. Over time, gravity pulls these enriched clouds together, triggering the collapse that leads to new star formation. In this way, the remnants of ancient stars become the building blocks of future worlds. What's truly awe-inspiring is the scale of this recycling system. It's estimated that much of the material in our own solar system, including the elements that make up Earth and even our bodies, was once part of a star that died billions of years ago. This means we are literally made of stardust, a direct result of the Milky Way's recycling process. Understanding this system sheds light on how the galaxy has evolved over time. It highlights the interconnectedness of all cosmic processes, from the birth and death of stars to the formation of planets and the potential for life. As we explore this galactic recycling system, we're reminded that the Milky Way is not just a static collection of stars but a dynamic, ever-changing ecosystem, constantly reinventing itself across the eons. Now turning to the hidden treasures within our galaxy, we explore the Milky Way's vast population of exoplanets, planets that orbit stars beyond our solar system. Astronomers estimate that there could be hundreds of billions of these worlds scattered across the Milky Way, with many more waiting to be discovered. This staggering number hints at the incredible diversity of planetary systems that exist, each with its own unique story to tell. Detecting these exoplanets is no easy task. Many of them are incredibly distant, and their faint light is often drowned out by the brightness of their host stars. Scientists rely on innovative techniques like the transit method, which detects a dip in a star's brightness as a planet passes in front of it, and the radial velocity method, which measures the slight wobble of a star caused by an orbiting planet's gravitational pull. Even with these advanced tools, finding smaller, Earth-like planets remains a significant challenge, as they are much harder to spot than their larger, gaseous counterparts. Despite these obstacles, the search for exoplanets has already yielded extraordinary results. Thousands have been confirmed, ranging from scorching hot gas giants to rocky worlds that may lie within their star's habitable zone, the region where conditions could support liquid water and potentially life. The discovery of these Earth-like planets is particularly exciting, as it raises the possibility that we are not alone in the universe. Consider Proxima Centauri b, the closest known exoplanet to Earth, located just over 4 light-years away. This rocky world orbits within the habitable zone of its star, making it a prime candidate for further study. While we don't yet know if it harbors life, its existence fuels our curiosity and drive to explore further. The hunt for exoplanets not only expands our understanding of the galaxy, but also challenges our perspective on our place in the cosmos. Each new discovery brings us closer to answering one of humanity's most profound questions: are we alone? As we continue to uncover the Milky Way's hidden worlds, we may one day find a planet that mirrors our own, offering a glimpse into the potential for life beyond Earth. Now shifting our gaze to the cosmic forces at play, let's dive into the Milky Way's cosmic rays, high-energy particles that streak through our galaxy at incredible speeds. These particles, mostly protons and atomic nuclei, carry energy far beyond what we can produce on Earth, and they play a significant role in shaping the galaxy's environment. Cosmic rays originate from some of the most violent and energetic events in the universe. Supernova, the explosive deaths of massive stars, are one of the primary sources. When a star explodes, it sends shock waves through space, accelerating particles to nearly the speed of light. Another potential source is the supermassive black hole at the center of our galaxy, Sagittarius, a star. Its immense gravitational pull and powerful jets could also be responsible for generating these high-energy particles. These cosmic rays don't just travel through space harmlessly, they interact with the galaxy's magnetic fields and gas clouds, influencing the formation of stars and planets. For example, they can ionize gas in star-forming regions, triggering the collapse of clouds into new stars. However, they also pose challenges for life, as their intense radiation can damage DNA and make space travel beyond Earth's protective atmosphere more hazardous. Scientists study cosmic rays using instruments on Earth and in space, such as the Pierre Auger Observatory and NASA's Fermi Gamma-ray Space Telescope. These observations help us understand not only the origins of cosmic rays, but also their broader impact on the galaxy's evolution. By unraveling the mysteries of these energetic particles, we gain deeper insights into the forces that shape the Milky Way and beyond. As we continue to explore the cosmos, cosmic rays remind us of the dynamic and ever-changing nature of our galaxy. From the explosive deaths of stars to the powerful influence of black holes, these particles are a testament to the incredible energy that flows through the universe. Now turning to the celestial rivers that weave through the Milky Way, we encounter the fascinating phenomenon of stellar streams. These streams are vast ribbons of stars flowing through our galaxy, often stretching across thousands of light years. They are the ghostly remnants of star clusters or dwarf galaxies that were torn apart by the Milky Way's immense gravitational pull. These stellar streams hold crucial clues about the galaxy's past. When a smaller galaxy or star cluster is disrupted, its stars are pulled into long, stretched-out arcs that eventually merge with the Milky Way. By studying the positions, movements, and compositions of these stars, astronomers can reconstruct the history of these ancient collisions. It's like piecing together a cosmic puzzle, revealing how the Milky Way has grown over billions of years by consuming smaller neighbors. One of the most well-known stellar streams is the Sagittarius Stream, formed from the remnants of the Sagittarius dwarf elliptical galaxy. This stream wraps around the Milky Way, offering a vivid snapshot of a long-ago galactic encounter. Other streams, like the Orphan Stream and the GD1 Stream, provide similar insights, each telling a unique story of disruption and assimilation. Understanding these stellar streams also helps scientists map the distribution of dark matter in the Milky Way. Since dark matter exerts gravitational forces but cannot be seen, the way these streams are distorted gives clues about where and how much dark matter exists. It's a window into the invisible scaffolding that holds our galaxy together. As we continue to uncover these cosmic trails, stellar streams remind us that the Milky Way is far from static. It is a dynamic, ever-evolving entity shaped by countless interactions over its long history. Each stream is a testament to the galaxy's past and a guide to its future, offering a deeper understanding of the forces that have shaped and continue to shape our cosmic home. Now shifting our gaze to the veiled corners of the Milky Way, we find ourselves immersed in the enigmatic world of dust clouds. These dense formations of gas and dust are scattered throughout the galaxy, often obscuring our view of the stars and cosmic phenomena beyond. Yet, far from being just cosmic obstacles, these clouds are the very cradles of stellar birth. Within these dark, swirling masses, gravity works its magic. As pockets of gas and dust collapse under their own weight, they heat up and begin to form new stars. These dust clouds are essentially the nurseries of the galaxy, where the raw materials of creation come together to ignite the fires of future suns. The Orion Nebula, one of the most famous star-forming regions, is a prime example of this process in action. However, these clouds also pose significant challenges for astronomers. Their thick, opaque nature can block our view of the galaxy's inner workings, making it difficult to study the stars and structures hidden behind them. To overcome this, scientists use specialized tools and techniques such as infrared telescopes, which can peer through the dust to reveal the secrets it conceals. Beyond their role in star formation, these dust clouds also play a part in the galaxy's chemical evolution. They contain complex molecules, including organic compounds, which are stirred and reshaped by the forces of the Milky Way. This makes them not just star factories, but also cosmic laboratories where the building blocks of life may be forged. As we continue to explore these cloudy realms, they remind us that even the most obscured parts of the galaxy hold vital clues to its story. They are both barriers and gateways, challenging our understanding while offering glimpses into the processes that shape the universe. In the grand tapestry of the Milky Way, dust clouds are threads of mystery and creation, weaving together the past and future of our cosmic home. Now peeling back another layer of the Milky Way's mysteries, we encounter one of the most baffling phenomena in modern astronomy: fast radio bursts. These incredibly brief but powerful bursts of radio waves last just milliseconds, yet they pack as much energy as the sun emits in days. First discovered in 2007, these bursts have puzzled scientists ever since, appearing as sudden, intense flashes in the vast radio silence of space. What makes these bursts even more intriguing is that some of them originate from within our own galaxy. While most fast radio bursts come from distant corners of the universe, a few have been traced back to sources closer to home, offering astronomers a rare opportunity to study them up close. One such burst, detected in April 2020, was linked to a magnetar, a highly magnetic neutron star right here in the Milky Way. This discovery provided crucial clues, suggesting that at least some of these bursts are caused by extreme magnetic activity. But the mystery doesn't end there. The origins of these bursts remain hotly debated. Some theories point to neutron stars, black holes, or even collisions between dense cosmic objects. Others suggest more exotic possibilities, like advanced civilizations communicating across the galaxy. While that may sound like science fiction, the truth is that these bursts challenge our understanding of the universe's most extreme environments. What fast radio bursts reveal is just as fascinating as their origins. They offer a unique window into the behavior of matter under extreme conditions, such as the intense magnetic fields around neutron stars. They also help astronomers map the universe's structure. As these bursts travel through space, they interact with cosmic material, providing insights into the distribution of gas and dust between galaxies. As we continue to unravel the secrets of these fleeting cosmic signals, they remind us of how much we still have to learn about our galaxy and beyond. Fast radio bursts are like cosmic whispers, hinting at the extraordinary events shaping the universe. And with every burst detected, we move one step closer to understanding the forces that govern our Milky Way. Now shifting our gaze to the vast cosmic clock, let's explore the concept of a galactic year, a timescale that highlights just how small we are in the grand tapestry of the universe. A galactic year is the time it takes for our Sun to complete a single orbit around the center of the Milky Way. This journey, spanning an astonishing 230 million Earth years, is a reminder of the immense size and slow, majestic rhythm of our galaxy. Think about this for a moment. Since the Sun was born, it has only completed around 20 orbits of the Milky Way. That's right, our solar system has circled the galaxy's core just about 20 times in its entire existence. To put it into perspective, the last time the Sun was in its current position, dinosaurs were just beginning to dominate the Earth. Over the course of one galactic year, our planet has seen the rise and fall of countless species, the shifting of continents, and the evolution of life from simple organisms to the complex ecosystems we know today. This cosmic timescale also underscores how fleeting human history is in the grand scheme of things. All of recorded human civilization, from the earliest agricultural societies to the modern technological era, has unfolded in less than a fraction of a galactic year. It's a humbling reminder of how much time has passed and how much more lies ahead in the Milky Way's slow, steady dance. As we ponder these vast stretches of time, it's worth considering what the next galactic year might hold. What will Earth look like when the Sun returns to this same position, hundreds of millions of years from now? Will life still flourish, or will the planet have undergone unimaginable changes? The galactic year not only connects us to the galaxy's past but also invites us to imagine its future, a future that, for now, remains as mysterious as the Milky Way itself. With this cosmic rhythm in mind, let's turn our attention to another fascinating aspect of our galaxy's structure, the web of connections that ties the Milky Way to the larger universe. As we venture deeper into the mysteries of the Milky Way, let's uncover its intricate ties to the cosmic web, the immense, invisible network that binds the universe together. Picture the cosmic web as a colossal spider's web, stretching across the cosmos, with galaxies like ours sitting at the intersections of its threads. These filaments, made of dark matter and gas, form the backbone of the universe's structure, guiding the movement and growth of galaxies over billions of years. The Milky Way isn't just floating in isolation, it's part of this vast cosmic tapestry. The web's filaments funnel gas and matter into galaxies, fueling the birth of stars and shaping their evolution. Without this intricate network, galaxies like ours wouldn't have the raw materials needed to form stars, planets, and ultimately, life. It's a delicate balance, one that highlights how interconnected everything in the universe truly is. Scientists study the cosmic web by mapping the distribution of galaxies and tracing the flow of gas between them. These observations reveal how the Milky Way is influenced by its place in the web, from its rotation to its interactions with neighboring galaxies. Even the motion of our solar system within the Milky Way is subtly guided by these cosmic threads. What's even more fascinating is that the cosmic web isn't static, it's dynamic, constantly evolving as galaxies move and the universe expands. Over billions of years, these filaments will continue to shape the destiny of the Milky Way, influencing everything from star formation to its eventual collision with the Andromeda Galaxy. As we reflect on the Milky Way's connection to the cosmic web, we're reminded of the grand scale of the universe and the unseen forces that shape it. This invisible network is a testament to the profound interconnectedness of all things, from the smallest atom to the largest galaxy. With this understanding of the Milky Way's place in the cosmic web, let's now look ahead to the final secret, a glimpse into the galaxy's future and the ultimate fate that awaits it. Turning our gaze to the horizon of cosmic time, we find ourselves pondering the ultimate destiny of the Milky Way. Our galaxy, vast and luminous as it may be, is not immune to the relentless march of the universe's evolution. One of the most dramatic events awaiting the Milky Way is its inevitable collision with the Andromeda Galaxy, our closest galactic neighbor. Billions of years from now, these two spiral giants will merge, their stars and gas clouds intermingling in a cosmic dance that will reshape both galaxies forever. This collision won't be a chaotic smash, but rather a slow, majestic merging, spanning hundreds of millions of years. The result, a new elliptical galaxy, often referred to as Milkomda, will emerge, marking the end of the Milky Way as we know it. But the story doesn't end there. As time stretches on, the Milky Way's star formation will gradually wane. The gas and dust needed to birth new stars will either be consumed or expelled, leaving the galaxy quieter and dimmer than it is today. The vibrant arms of our spiral galaxy will fade, and the once bustling star factories will fall silent. Even the supermassive black hole at the Milky Way's heart will play a role in its transformation. Over eons, it may grow larger, consuming surrounding material and influencing the galaxy's structure. As the universe continues to expand, the Milky Way will become increasingly isolated, drifting farther from other galaxies in the vast cosmic void. Yet, in this quiet future, there's a strange beauty. The Milky Way's transformation into Milkomda and its eventual fading are not endings but part of a continuous cycle of cosmic change. Galaxies are born, evolve, and merge, their stories woven into the fabric of the universe. As we contemplate the Milky Way's future, we're reminded of the impermanence of all things, even on a galactic scale. This final secret invites us to marvel at the grandeur of time and the ever-changing nature of the cosmos, leaving us with a sense of awe and curiosity about what lies beyond. With this glimpse into the Milky Way's fate, we've journeyed through 25 secrets that reveal the wonders and mysteries of our galaxy. Each discovery reminds us of the incredible complexity and beauty of the universe we call home. As we bring our cosmic journey to a close, it's worth reflecting on the incredible tapestry of secrets we've uncovered about the Milky Way. From its invisible halo of dark matter to its future collision with Andromeda, each revelation has painted a picture of a galaxy that is as mysterious as it is magnificent. We've explored the supermassive black hole at its heart, marveled at its spiral arms, and even traced the paths of stars racing through its vast expanse. These 25 secrets remind us that the Milky Way is not just a collection of stars but a dynamic, evolving entity, teeming with stories waiting to be told. The beauty of these discoveries lies in their ability to connect us to something far greater than ourselves. They invite us to look up at the night sky with a deeper sense of wonder and curiosity. Which of these secrets captivated you the most? Was it the galactic cannibalism that shaped our galaxy, or perhaps the hypervelocity stars racing toward the unknown? Share your thoughts in the comments below. We'd love to hear which secret sparked your imagination. If you've enjoyed this journey through the Milky Way's mysteries, don't forget to subscribe and hit the notification bell. There's a universe of cosmic revelations waiting to be explored, and we're just getting started. Thank you for joining us on this voyage through the stars, and until next time, keep looking up. The cosmos has so much more to reveal.